Okay, so here is the differential equation that we want to solve. If we kind of want to match it up with the P, Q, and R stuff from the more general equation that I wrote in the previous video, notice that P of t is equal to 1, Q of t is equal to 0, and R of t is equal to 1. Now, P of t is always equal to 1, meaning it's never equal to 0. So every point is an ordinary point. So by the fact that I mentioned in the previous video, I can expand x, the solution to this differential equation, as a power series centered at any point. And I'm just going to pick t naught is equal to 0. So, but again, by the fact in the previous video, which I haven't proven, we'll kind of look at a proof a little bit later, I can write the solution as a power series centered at 0. So t minus t naught is just t, and it's t to the power of k. Okay, what I'm going to do now is I'm going to plug this expression for x into this differential equation and see what it tells me about the coefficients ak. So remember, we computed in the last video that x double prime of t is the sum k equals 2 to positive infinity k times k minus 1 ak t to the power of k. Now observe what happens when I plug it into the differential equation. So I'll have x double prime, which is the sum k equals 2 to positive infinity k times k minus 1 ak, oh, this should be t to the k minus 2, t to the k minus 2 plus x, which is k equals 0 to positive infinity ak t to the k, and this is equal to 0. Now what I want to use is the following fact. I'm going to erase this fact, so write it down. If I have a series, a power series, of the form bk t to the power of k, and this is identically equal to 0, this implies that all of the bk's are equal to 0. And so that's what I'm going to do. So I want to write this series, the series that I have, I want to write that series as like one series, and that's going to imply all of the coefficients are equal to 0. So that's going to be the next thing that I do. But in order to do that, I need to do a re-indexing there, because instead of having t to the power of k minus 2, it needs to be t to the power of k. So I'm going to introduce kind of a transition variable, n is equal to k minus 2. If n is equal to k minus 2, this means k is equal to n plus 2. And so this sum right here, if I re-index, well, what's going to happen? K is equal to n plus 2, so that k is going to be n plus 2. K minus 1, that's going to be n plus 2 minus 1, so that'll be n plus 1. AK will be a n plus 2, and importantly is going to be t to the power of n. Now what about the lower limits? So you might realize this is very similar to doing U substitution. So the lower limits start from k is equal to 2, and so if k is equal to 2 and n is equal to k minus 2, the lower limit in terms of n will be 0, and it's still going to go up to positive infinity. Okay, so now what we're going to do, notice n is just a summation variable. We can call it n or k or whatever we want, and so we're going to call it k instead of n. And when we do that, this is the series, or the sum, k equals 0 to positive infinity k plus 2 times k plus 1 ak plus 2 t to the power of k. And so now I'm just going to rewrite this expression with these new indices. So when I just rewrite this with the new index, the first series is this series k equals 0 to positive infinity k plus 2 k plus 1 ak plus 2 t to the power of k, and then the other series that just stays the same. This is k equals 0 to positive infinity ak t to the power of k, and that's equal to 0. And so now what we're going to do, again, we want to make this just as something times t to the k, or the terms being something times t to the k, and so we're going to combine these two series and get the sum k equals 0 to positive infinity k plus 2 k plus 1 ak plus 2 plus ak t to the power of k is equal to 0. And so now we can conclude the thing that we want to conclude, which is the coefficients are, all of those coefficients are equal to 0. Again, if a power series is identically equal to 0, so notice the right-hand side is always 0. It doesn't matter what t is, the right-hand side is always 0. And if we know a power series is identically equal to 0, the only way that can happen is if the coefficients are all equal to 0. Okay, so what this tells us is k plus 2 times k plus 1, ak plus 2 plus ak is equal to 0. Okay, now this is kind of step 1 in these problems. The whole sort of step 1 is to get some relation like this that relates the coefficients to each other. And in the next video, we'll see how we can solve for these coefficients.